Good morning, good afternoon. Okay, so in this example, we will speak about friction. Okay, so it's a good example to review. So the question is to find the force P, the largest force P, before motion occurs. So motion occurs, what does that mean? It means either the block A slip to the right, either the block B, it cannot slip to the right because it is attached at T, but it can rotate. Maybe the block A could even maybe rotate, but where the rope is attached, it will be difficult, but we can look at tipping too for that. Some data that we know that the block A has a mass of 7 kilograms, so the block A, 7 kilogram, and the mass of the block B, it's 10 kilogram. Okay, so the first steps, I always advise for the first steps to do free body diagrams and to look at the different forces. So let's try to do all the free body diagram just below the images. So we have the block B. Don't make your body too small because of that it will be very hard to see. So that's the block B. And we have the block A. Oops. Block B, block A a little bit longer. And the pulley C and the pulley D. Okay, let's draw the forces on that. The forces in blue, the forces that we know. So block B, we have a weight in the middle, WB, and it's equal to 10 times, so WB is equal to 10 times 9.81. So 98.1. And at the block A, we have the weight of the block A that is equal to 7 times 9.81. Grab my calculator at the same time. 7 times 9.81. So this is 68.67. That's Newton. Newton. Okay. And after that, all the other forces, we don't know them. So let me write them in red. Block A, let's look at the block A first. We have, so the force P is going down. So we have a force P that is going down. Let's call that the P final. And on this side, we have a force that I will call PD. Okay. It's not the same because there's some friction in the pulley. PD on this side, PD on the other side. And on the right, a force PC. And same, different because we have friction in the pulley. So let's write the coefficient of friction. Mu D equals 0.1 and mu C is equal to 0.4. This PC is the same forces than this one, PC. Okay, so for the direction of the friction, the block A is going to the right, tend to go to the right, so the force of friction is going to the left on both sides. Let's call that force of friction FF on the block A, and this one FF on the block B. So this force of friction FFB is the same as this one, but in the opposite direction, like this. And normal force, let's just use another color because we have a lot of information on this free body diagram. So let's put the force NA. We don't know where, but somewhere below. And we have NB, NB. Let me just change my mind for one thing. Let me draw the force NB on this side and NB on this side. And one more force that we don't know, that's the tension there on the top. Let's call that T. I think I have all my unknown. Okay. And some dimension. we have the 400 millimeter and the 300 millimeter. Here we go. And we have two coefficients of friction. We have the mu A equals 0.3 and the mu B on the top, that's equal to 0.4 between the boxes A and B. A lot of information, but we will be good. Okay, so what can we do to begin to solve? I will begin with the block B. Why? Because at the block B, we have some information. We have the weight WB. And how many unknowns do we have? 1, 2, and 3. And we have 3 equations. The force on X, the force on Y, and either the equation of friction if it's slipping, or either the equation of moment if it's tipping. So let's do first scenario. Block B is slipping. And what I mean slipping, or I should say block A is slipping on B. Block A is slipping on or below B. Okay? So let's do that. That's the first scenario. So when the block A is slipping, the first expression that we will use is the sum of the forces on the Y. It's equal to 0 on the block B. So we are on block B. Okay. Let me write it. So that's, we use the free body diagram of the block B and the equation of equilibrium on the block B. So sum of the forces on the Y, it's equal to 0. We have, so we will use X and Y. So we have minus W B plus NB, it's equal to 0. So NB, it's equal to 98.1 Newton. Okay. Now we assume it's slipping. So we have force of friction at B, that is equal to mu B times NB. So it's equal to 0.4 times 98.1. So the force of friction at B is equal to 0.4 times 98.1, 39.24 Newton. Okay. So 1, 2, and third equation, sum of the forces on X is equal to 0. So when we do sum of the force on X equals 0 on the block B, we have minus T. And we have plus FFB. It's equal to 0. So it means that T is equal to 39.24. I try to use the maximum at the space that is available. So first possibility, T equal 39.24. Let's check. Is it possible that the block B and A are slipping? Like the block A is slipping below the block B? Check. I call that a check. Oops. If it's slipping, the force of friction and the normal force are below the block. So this is somewhere there, right? Somewhere below. So let's find the distance X if the normal force is still below. So let's find this little X there. For that, we will use the moment about, let's call this point B. So if I do sum of the moment about B, it's equal to 0. We have the distance X times WB, and that's a negative moment. And we have plus the distance of 400 millimeter times T, it's equal to 0. So we have X that is equal to 400 times T, that is equal to 39.24, and divided by WB. WB is 98.1. So X is equal to 400 times 39.24 and divided by 98.1. That's 160, and that's millimeter because 400 is in millimeter. So now let's compare this distance x with the size of the box. The size of the box is 300 millimeter. This is more than 150 millimeter. So it's not possible that the box is slipping, because if it's slipping, the normal force is outside the bottom of the box. So let's check if it's tipping. Second scenario. I need to get enough space. So let's try the second scenario. The block on the top, block B, is tipping. Block B is tipping. So I'm still looking at the block B, okay? So now if it's tipping, it means that, let me use another color, maybe in orange. It means that the NB is just there, just on the corner. So you see, if A going to the right, this one will tend to rotate in this direction, and the last contact will be with the corner B. Okay. So block B is tipping. We have NB, we have FFB, and we have T. So let's use sum of the moment about B. It's equal to 0. So what we have the distance 150 millimeter. So that's half of the distance from W, time WB, and that's a negative moment, plus T time the vertical distance, the 400, it's equal to 0. Okay, it's a time. So it means that T it's equal to 150 times WB 98.1 and divide by 400. So it means that T it's equal to 150 times 98.1 divided by 400. That's 36.79 Newton. And you see, it's less than the force T. Oops. Than this one. So it means that it's tipping. Okay, when it's tipping, the force for friction is not necessary, it's not the maximum force of friction. So we need to find the force of friction. So for that, we will use sum of the forces on x equals 0, still on the block B. And we have minus T plus FFB. That is equal to 0. So the force of friction, it's equal to T. So it's equal to 36.79 Newton. So we have our force of friction. And we need also NB, because we will need to put NB on the block A after that. So for the block NB, we do sum of the forces on Y, it's equal to 0. So we have minus WB, and plus NB, it's equal to 0. So NB, it's equal to WB 98.1 Newton. And we can use those two forces for the free body diagram of the block A. Almost there. Let me go a little bit to the left, so I will have some space. Okay, just before going to the left, let's write below what we found. We found that FB it's equal to 36.79 Newton, and we found that NB it's equal to 98.1 Newton. Okay, so now we will use the free body diagram at A, but we have some new information. So let me read you the free body diagram at A. Bigger there. We know that WA it's equal to 68.67. We know that NB is just on this side, just on the corner, and NB is equal to 98.1. We can write the distance. We know that it's 150 millimeter. Right? We know the force of friction going to the left, FFB, and FFB it's equal to 36.79 Newton. and the forces that we don't know, PC and A, somewhere below, and FFA. Okay, let's do the first. Oh, sorry, I have a little one close to me. Okay, let's find NA because anyway, NA will be the same if it's sleeping or if it's sleeping. So NA. When we do sum of the forces on Y equals 0, we have minus WA, we have minus NB plus NA, it's equal to 0. So NA is equal to, so WA is 68.67. Try to take your exact number. And B is 98.1. So this is equal to 166.77. Now, let's do the force of friction. Let's assume it's slipping. Slipping block, that's a block A. Block A is slipping on the ground. Okay, block A is slipping. So force of friction AFA is equal to the mu A times NA. So it's equal to 0.3 times 167.77. So this is, oops, times 0.3. Take the coefficient of friction that is below. So this is FFA. It's equal to 50.0 Newton. Okay, we don't know this dimension there, so it's hard to check if it's tipping. Let's do now the sum of the forces on X is equal to 0. Okay, so sum of the forces on X equals 0. What do we have on X? We have minus FFB, because it's going to the left, plus the force in the rope to the pulley, and minus FFA, it's equal to 0. So PC, it's equal to 36.79 plus 50.0. PC, it's equal to 86 point, let's say 8. Oops, let's see. Okay, so if we want to do the tipping, we are missing some information for this example. We need this distance. We need the half of the distance below, but the block is so wide and this H is very low, so it will not tip. I think that there are assumptions. So now we have PC. So this is the force PC. We need to come back on our pulley. So we have the force PD, that is equal to the force PC times the exponential of the angle, that is pi divided by 2, times the mu, that is equal to 0.4. So PD, it's equal to, so you take the PC, that is equal to 86.8, and I forget my my decimals, time the exponential of, so pi, oops, okay, pi times 0.4 divided by 2. This is 162.7 Newton. And now let's make it in green. So this was the pulley, and now P, the final force P, is equal to PD. My little one begins to be tired. So this angle is pi. That's a, oh, 10 seconds, please. This is pi times 0.1. So the force P is equal to 162.7 times the exponential of, and power pi times 0.1. This is 223 Newton. Here we go. We are the final force. So that was a long problem, but very interesting, right? So we try tipping, slipping. Let me see if we can go back on all the steps that we did. That was a long video, sorry, but worth it. Oops. Here we go. So let's come back on the steps. Free body diagrams, that's the key. Free body diagrams, including the pulley, everything, right? After that, we work with the block on the top, with the block B. We assume it was sleeping. We check it's not sleeping, so we found that yes, in fact, it's tipping. And after that, with the force of friction B and B, we did the free body diagram of the block A. That is also this one. And we assume this is sleeping because it's very large, very wide. And we are missing some information to check, but it's tipping, it's sleeping. We found P, the P attached to the block. And after that, we come back on the pulley. Pulley at C, angle of pi divided by 2, force of friction of 0.4, coefficient of friction of 0.4 in the pulley. And after that, the pulley at D, angle pi, because it's a semicircle, and mu equals 0.1. So exponential of pi times 0.1. And for the very last steps, we find P equal to 23 Newton. Here we go. So that was the problem of review for friction. See you in the next video. Bye-bye.